Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of numerical problems on three-phase induction motors having double cage rotors. By solving these problems, we shall learn how to calculate power developed and torque produced at the time of starting and at certain value of slip from the approximate equivalent circuit. For this purpose, we shall neglect magnetizing current, stator impedance, and mutual reactance between two cages. Let us have a look at the equations we shall use today to solve the numerical problems. Let the stator impedance per phase be Z1 equals to R1 plus JX1. Outer cage impedance per phase referred to stator side Z0 dash equals to RO dash by S plus JXO dash, and inner cage impedance per phase referred to stator side Zi dash equals to Ri dash by S plus Jxi dash. Equivalent rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus Jx2S dash, that is equal to Z0 dash in parallel with Zi dash. This may be written as Z0 dash into Zi dash divided by Z0 dash plus Zi dash. Total equivalent impedance per phase ZDQ equals to Z1 plus Z2 dash. Stator current per phase I1 equals to V1 by ZDQ, where V1 is the applied stator voltage per phase. If we neglect magnetizing current, I1 is approximately equal to I2 dash. Rotor current per phase referred to stator side I2 dash equals to E2S dash by Z2 dash, where rotor induced EMF per phase at standstill condition referred to stator side E2S dash equals to V1 minus I1 into Z1. Power developed per phase PD equals to I2 dash square into R2 dash by S. For three-phase induction motors, total torque developed TD equals to 3 times PD divided by omega S, where omega S is the angular speed of rotating magnetic field measured in radians per second. Omega S equals to 2 pi ns by 60, where ns is the speed of rotating magnetic field measured in revolutions per minute. When we neglect the stator impedance, the total equivalent impedance per phase ZDQ becomes approximately equal to Z2 dash, which is the equivalent rotor impedance per phase referred to stator side. The cages of a double cage induction motor have standstill equivalent impedances referred to the stator side of 3.5 plus J 1.5 ohm and 0.6 plus J7 ohm respectively. The full load slip is 6%. Neglecting stator impedance and magnetizing current, we have to find the starting torque at normal voltage in terms of full load torque. Let us first write down the given data. At standstill condition, outer cage impedance per phase referred to stator side ZOS dash equals to RO dash plus JXO dash, that is equal to 3.5 plus J 1.5 ohm. This may be written in polar form as 3.8079 ohm at an angle 23.1986 degree. Inner cage impedance per phase referred to stator side ZIS dash equals to RI dash plus JXI dash, that is equal to 0.6 plus J7 ohm. This may be written in polar form as 7.0257 ohm at an angle 85.1009 degree. Let us first determine ZOS dash plus ZIS dash, that is equal to 4.1 plus J 8.5 ohm. This may be written in polar form as 9.4372 ohm at an angle 64.2495 degree. Let us now determine equivalent rotor impedance per phase referred to stator side. Z2S dash equals to R2 dash plus JX2S dash, that is equal to ZOS dash in parallel with ZIS dash. This may be written as ZOS dash into ZIS dash divided by ZOS dash plus ZIS dash. Using values we get 3.8079 at an angle 23.1986 degree into 7.0257 at an angle 85.1009 degree divided by 9.4372 at an angle 64.2495 degree. That gives us 2.8349 ohm at an angle 44.05 degree. When running with sleep, S equals to 6%, that is equal to 0.06. Outer cage impedance per phase referred to stator side, ZO dash equals to RO dash by S plus JXO dash, that is equal to 3.5 by 0.06 plus J 1.5 ohm. That gives us 58.3333 plus J 1.5 ohm. This may be written in polar form as 58.3526 ohm at an angle 1.473 degree. Inner cage impedance per phase referred to stator side, Zi dash equals to Ri dash by S plus Jxi dash, that is equal to 0.6 by 0.06 plus J7 ohm. That gives us 10 plus J7 ohm. This may be written in polar form as 12.2066 ohm at an angle 34.992 degree. Let us now determine ZO dash plus ZI dash, that is equal to 68.3333 plus J 8.5 ohm. This may be written in polar form as 68.86 ohm at an angle 7.0906 degree. Equivalent rotor impedance per phase referred to stator side, Z2 dash equals to R2 dash by S plus JX2S dash, that is equal to ZO dash in parallel with ZI dash, which is equal to ZO dash into ZI dash divided by ZO dash plus ZI dash. Using values we get 58.3526 at an angle 1.473 degree into 12.2066 at an angle 34.992 degree divided by 68.86 at an angle 7.0906 degree. That gives us 10.344 ohm at an angle 29.3744 degree. We have computed at standstill condition equivalent rotor impedance per phase referred to stator side, Z2S dash equals to R2 dash plus JX2S dash equals to 2.8349 ohm at an angle 44.05 degree. This may be written in Cartesian form as 2.0375 plus J 1.971 ohm. Power developed per phase PDS equals to I2S dash square into R2 dash, that is equal to E2S dash by Z2S dash whole square into R2 dash. For three-phase induction motor, starting torque TDS equals to 3 times PDS divided by omega S, where omega s is the angular speed of rotating magnetic field in radian per second. When running with sleep, S equals to 6% or 0.06. Equivalent rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus J X2 S dash, that is equal to 10.344 ohm at an angle 29.3744 degree. This may be written in Cartesian form as 9.0141 plus J 5.0739 ohm. Power developed per phase PD equals to I2 dash square into R2 dash by S, that is equal to E2S dash by Z2 dash whole square into R2 dash by S. Full load torque TD equals to 3 times PD divided by omega S. At normal voltage, starting torque in terms of full load torque TDS by TD equals to Z2 dash by Z2S dash whole square into R2 dash divided by R2 dash by S. Using values we get 10.344 divided by 2.8349 whole square into 2.0375 divided by 9.0141, that gives us 3:1. This result indicates that the starting torque is 3 times larger than the full load torque at normal voltage. A 440 volts 3-phase star-connected double-cage induction motor has standstill impedance per phase referred to the stator side of the outer and inner cages 0.5 plus J 0.15 ohm and 0.06 plus J 0.6 ohm respectively. Neglecting stator impedance and mutual reactance between two cages, we have to calculate power developed by the motor at starting and at full load with 4% slip. Let us first write down the given data. Line to line stator voltage VL equals to 440 volts. Since the stator winding is star connected, stator voltage per phase V1 equals to VL by root 3, that is equal to 440 divided by root 3, that gives us 254.0341 volts. At starting, outer cage impedance per phase referred to stator side ZOS dash equals to RO dash plus JXO dash, that is equal to 0.5 plus J 0.15 ohm. This may be written in polar form as 0.52202 ohm at an angle 16.6992 degree. Inner cage impedance per phase referred to stator side ZIS dash equals to RI dash plus JXI dash, that is equal to 0.06 plus J 0.6 ohm. This may be written in polar form as 0.60299 ohm at an angle 84.2894 degree. Let us now calculate ZOS dash plus ZIS dash. Using values we get 0.56 plus J 0.75 ohm. This may be written in polar form as 0.936 ohm at an angle 53.2525 degree. Equivalent rotor impedance per phase referred to stator side Z2S dash equals to R2 dash plus JX2S dash, that is equal to ZOS dash in parallel with ZIS dash, which is equal to ZOS dash into ZIS dash divided by ZOS dash plus ZIS dash. Using values we get 0.52202 at an angle 16.6992 degree into 0.60299 at an angle 84.2894 degree divided by 0.936 at an angle 53.2525 degree. That gives us 0.33629 ohm at an angle 47.7361 degree. When running with slip, S equals to 4% or 0.04, outer cage impedance per phase referred to stator side Z0 dash equals to RO dash by S plus JXO dash, that is equal to 0.5 by 0.04 plus J 0.15 ohm. That gives us 12.5 plus J 0.15 ohm. This may be written in polar form as 12.5009 ohm at an angle 0.68752 degree. Inner cage impedance per phase referred to stator side Zi dash equals to Ri dash by S plus Jxi dash, that is equal to 0.06 by 0.04 plus J 0.6 ohm. That gives us 1.5 plus J 0.6 ohm. This may be written in polar form as 1.6155 ohm at an angle 21.8014 degree. Let us now determine Z0 dash plus Zi dash. Using values we get 14 plus J 0.75 ohm. This may be written in polar form as 14.0201 ohm at an angle 3.0665 degree. Equivalent rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus JX2S dash, that is equal to Z0 dash in parallel with Zi dash, which is equal to Z0 dash into Zi dash divided by Z0 dash plus Zi dash. Using values we get 12.5009 at an angle 0.68752 degree into 1.6155 at an angle 21.8014 degree divided by 14.02021 at an angle 3.0665 degree. That gives us 1.4405 ohm at an angle 19.4224 degree. Given stator voltage per phase V1 equals to 254.0341 volts. At starting, we have computed equivalent rotor impedance per phase referred to stator side Z2S dash equals to 0.33629 ohm at an angle 47.7361 degree. This may be written in Cartesian form as 0.2262 plus J 0.2489 ohm. Rotor current per phase referred to stator side I2S dash equals to V1 by Z2S dash. Using values we get 254.0341 divided by 0.33629. That gives us 755.3943 ampere. Let us now calculate total power developed. PDS equals to 3 times I2S dash square into R2 dash. Using values we get 3 into 755.3943 square into 0.2262. That gives us 387.18 into 10 to the power 3 watts or 387.18 kilowatts. When running with slip, S equals to 4% or 0.04, equivalent rotor impedance per phase referred to stator side Z2 dash equals to 1.4405 ohm at an angle 19.4224 degree. This may be written in Cartesian form as 1.3585 plus J 0.479 ohm. Rotor current per phase referred to stator side I2 dash equals to V1 by Z2 dash. Using values we get 254.0341 divided by 1.4405, that gives us 176.3522 ampere. Let us now determine total power developed. PD equals to 3 times I2 dash square into R2 dash by S. Using values we get 3 into 176.3522 square into 1.3585, that gives us 126.75 into 10 to the power 3 watts or 126.75 kilowatts. So today we have solved a couple of numerical problems on three-phase induction motors having double cage rotors. By solving these problems, we have learned how to calculate power developed and torque produced at the time of starting and at certain value of slip from the approximate equivalent circuit. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.